See how it works in another type of example. X times ln of x. The claim is that, this is section 7.1, so it's baked in that the method to use is integration by parts. But picture this as an exam question. You have substitution hanging out as a different method. You could try it. Try u equals ln x and go through the substitution process. It won't work out very well. But if you try integration by parts, we try to identify that this expression is equal to uv minus the integral of v du. That requires that u is equal to part of x ln of x dx, and dv equals the rest of that. So we have two options. Option 1. Now keep in mind the dv and the dx, they always go together. The u is never going to contain dx. dv always contains the dx term. So option 1 is u equals x. dv equals everything else, ln of x dx. Option 2. If that doesn't work, we'll try the other way. We'll try to let u equal ln of x. And then dv is going to be x dx. Everything has to be accounted for. You must always have u times dv equals x ln of x dx. Everything must be accounted for. We can't be missing any pieces, and we can't have any extra pieces. And notice that in both these options that happens. We have the x, the ln of x, and the dx when we multiply the two parts together. Okay, so I'll draw a line through these and see where it takes us. So first option. If u is equal to x, then du by dx is equal to 1. So du is equal to dx. And then we're going to have to integrate. Every time we do this, when we integrate dv, we're always going to get v. On the right hand side, we integrate ln of x. Which can be done, but it isn't something that you have memorized. It's not memorized. It's not on your list. Okay, so at this point, once you have a dv that you can integrate, try the other option. Okay, so let's try the other option. We have integral of x, ln of x dx. We're going to rewrite this as uv minus the integral of v du. And we have to get the pieces. So if u is equal to ln of x, then du by dx, we take the derivative of ln of x, we get 1 over x. Cross multiply. Du is dx over x. Okay, now for dv, integrate both sides. We get v is equal to the integral of x dx. And that's an integral we can do by memory, or by using a simple rule, the anti-power rule. 1 over 2x to the 2 plus c, but we'll suppress the plus c. Now plug in all the ingredients. So u, we said was ln of x. V we just found was 1/2 x squared. minus integral of v, which is 1/2 x squared, and then du is dx over x. And to clean things up a little bit, we have 1/2 x squared ln of x, the x squared in front of the ln, and a common factor 1/2 out, then use exponent laws. We have x to the 2 divided by x to the 1, we just have an x. And what we've done, what we've accomplished, is we've replaced the integral of x ln x with an integral of x. Definitely better. Good application of integration by parts. But we have to do it again, and we have to integrate now. We can integrate this. We have 1/2 x squared ln of x minus antiderivative of x is 1/2 x squared. And now we'll put a big plus c, and we can clean up a little bit. Ran out of space below, so I'll continue to the right. We have 1/2 x squared ln of x minus 1/4 x squared plus c. That would be our answer, which I think is a nice answer. Now, option 1 in this case wasn't a dead end, because we saw earlier that ln of x has an antiderivative. The antiderivative of ln of x is x ln of x minus x. And we could, if we had that memorized, we could have substituted that in and found a roundabout way to solve the problem. But I don't think you would have liked it. You can try it, but you won't like it. Okay, before going on to the next problem, you should be asking yourself, how much time am I going to waste using method 1 and method 2 for every single one of these if half the time it's the one I don't start with? Am I going to have time to do every single problem 2 different ways? Or half the problems 2 different ways, because half the time you're going to get it right the first time. And the answer is no. So see this thing down here, practice tells you what to do. There's also a cute acronym. Acronym usually works. For this class, it will always work. And there's a last page on Dr. Meredith's notes that are posted alongside these videos that gives a summary of the different types of integrals that you're going to face in this course that require integration by parts. And this acronym is perfectly compatible with that summary page. The acronym is the word late. The L stands for logs. The A stands for algebraic. So that's something like x to the n. The T stands for trig. And the E stands for exponential. What this acronym tells you is which part to set equal to u. Here's how it works. So let's say we have an integral of x times the sine of x dx. This contains both an a term and it contains a t term. A comes first in late. It appears first in the acronym. Let u equal x. Okay, what if we do x times ln of x? Well, here we have an a and we have an L. And L comes first in late. So we let u equal ln of x. There is absolutely no cosmic reason for this to happen. It's just, if you have a small amount of data, you can find a cute way to explain the data that has like no reason for it. And this is just a cute way to explain the process for selecting which thing to equal u to and which thing to equal v. Now, I put here usually works. Some of you are going to be enthralled by this course, and you will take Calc 1000 next, and you might even be enthralled by that course. And then you'll take Calc 1301 or Calc 1501, and in that course you will find why the word usually is there. Because there's some that it will not work for, and there's still problems that can be solved by integration by parts. Okay. So, for this problem, antiderivative of x times e to the 2x dx. Let's see what the late acronym prescribes to us as a course of action. So the late acronym, LATE. What we have here is we have an exponential, so we have an e, and we have an algebraic, we have an a. The a comes before the e, so we're going to let u equal x. That means dv has to equal everything else. dv is going to be e to the 2x dx. Again, the dx and the dv always go together. They're always a pair. All right. So if we transform this integral using integration by parts, what we'll get is uv minus the integral of v du, a formula you must memorize. And plug in the pieces, some of them at least. U is x. V you'll have to find, leave a space for it. Minus the integral of v du. I don't have either of those things, we have to find them. So let's get the first thing, let's get the du. Du by dx is 1. So du is equal to dx, we cross multiply, so we can put that in, dx right there. Okay, now we need to integrate v. Integrate dv to get v. V is the integral of e to the 2x dx. Use substitution. Substitute w equals 2x. The reason why I use w for substitution is revealed at long last. And what you'll find, basically I don't want to have u appearing twice in the same problem in different ways. So after going through the substitution process, you'll find that v is 1/2 e to the 2x. Now sub in that in both pieces, 1/2 e to the 2x, 1/2 e to the 2x. Okay, and we can clean up the integral. 1/2 x e to the 2x minus 1/2 integral e to the 2x. Okay, we do a substitution. But before doing that, notice that we started with x times e to the 2x in the integral. Now we just have e to the 2x. The x disappeared, so this is definitely better. This is a nice integral. This is something from 6.4. Let u or w, I'll use w now, equal 2x. Wow. So dw by dx is 2. dw is equal to 2 times dx. So dx is dw over 2. So that's the substitution that would have been done up above. Same substitution. So 1/2 x e to 2x minus 1/2 times integral e to the w, and the dx gets replaced by dw over 2. And then we can clean that up. So 1/2 x e to the 2x minus 1/2 times 1/2, so 1/4, 1 over 4, integral e to the w dw, antiderivative of e to the w is just e to the w plus c. And then we undo the substitution, replace it back with the 2x. And if you really must, if you have to, you can use the letter u there for the substitution. Just don't get confused when you're deciding, okay, is this a u for integration by parts or is it a u for substitution? If you can keep track of that, then feel free to use the letter u here. If you're worried about mixing it up, then reserve w for your substitutions at this point. And then uv are for integration by parts. Okay, and this could have been mentioned in the last two examples, but it's worth mentioning here anyway. It is the fact that every one of these, like all antiderivatives, can be tested. You can test it by taking the derivative. The first part will require a product rule, and then what you would check for is after taking the derivative, it's simplifying. Stuff will cancel out and you'll get x times e to the 2x. If it doesn't happen, it means you made a mistake. Okay, next one. How do you do this? X times ln of x to the power of 2. Well, it worked so far. Let's try it again. Let's try the late acronym, LATE. Because we have an algebraic term and we have a log term. And L comes before A. So we should let U equal ln of x all to the power of 2. We have to account for everything. We can't just say u is equal to ln of x. It has to be a whole block that we let equal to u. Everything must be accounted for. So if u is equal to that, then dv is equal to leftovers, which in this case, we haven't accounted for the x, and we haven't accounted for the dx. Then we multiply these two things together, we get the original thing that comes after the integral. So our integration by parts, our formula says that we're replacing the integral of u dv with uv minus the integral of v du. Okay, we can plug in a few of the pieces. I think I need more space for this one, so I'm going to cram things in. I think this is, we'll see what happens. I can't remember. So we have ln of x all squared times the block I'll leave for dv minus the integral of v du, so I don't know what that's going to be. Let's see. So for the u part, when I take the derivative with respect to x, guess what we need to use? We need to use a chain rule. This is a function of the power of 2. The 2 is going to come down. We're going to have our function to one lower power. So ln of x to the power of 1. Multiplied by the derivative of the inside. The derivative of ln of x is 1 over x. I'm going to clean this up a little bit. This is 2 times the ln of x divided by x. And then we can cross multiply. So du is 2 ln of x dx over x. So that's our du term. Now we have to find the v term. V is the integral of x dx. And we get 1/2 x squared. And as in other examples, we'll suppress the plus c for now. So 1/2 x squared, 1/2 x squared. Okay. Some interesting things happen. The 2 downstairs and the 2 upstairs cancel. We have an x and an x squared that will partially cancel. We'll do some cleanup. 1/2 x squared times ln of x, all power 2, minus, no constants come out. We have an x over x squared over x. An x upstairs survives. We have x times ln of x dx. And is it better? We had x ln of x squared, now it's x ln of x not squared. I would argue this is better. But not automatic. We have to keep going. I'm going to do this integral off to the side. Integral of x. Well, maybe not. I'll do it in line. We need integration by parts again. This is not something you can solve by substitution. You can't you can't do a substitution method without basically transforming it into a different integral that requires integration by parts. The late acronym. So we're going to do IBP again. Late acronym says to again let u equal ln of x. So it's an a term, an algebraic term appears, and a log term appears, but L comes before a in the acronym, so that's what that u equal to. So 1/2 x squared times the ln of x squared minus, we gotta leave a big space for what's about to get subtracted. We're going to have uv minus the integral of v du. One half x squared times ln of x all squared minus, so u times v, we have a ln of x term for u, So u is equal to ln of x. And then I have to leave a space for v. Minus times minus, so plus. That minus distributes through. Integral of v du. You have to leave a space for those two terms. Okay, so u is equal to ln of x. Du by dx is 1 over x. So du is equal to dx over x. If u is equal to ln x, then dv must be equal to everything else. dv must be equal to x dx. This looks familiar. I think we did this already in an earlier example. We'll do it again. It's okay. So that's our v 1/2 x squared. So ln of x times 1/2 x squared. And v 1/2 x squared times du, which is dx over x. Okay. 1/2 x squared times the ln of x all squared minus 1/2 x squared times the ln of x plus 1/2 x squared over x cancels, just give us an x. And we can finally just use an anti-power rule and not do integration by parts a third or fourth or fifth time, just twice for this one. One half times 1 over 2x squared, and a big plus c. And the last step, simplifying. Just going to copy those first two terms. I don't need to change anything. And the last term, the only thing to change is 1/2 times 1/2 is a quarter. Simplify that. 1 over 4x to the 2 plus c. So I'm a big advocate for checking your answers for most problems. Here's one where I wouldn't check. I just say, if it's wrong, I don't have time to fix it. Took too long. And even if I check it and it doesn't match up, it could equally be likely that I made a mistake taking the derivative instead of integrating. It's just you're asking for disaster. So this one, don't bother checking ones that look like this. But this type, not too bad to check. Previous type, not too bad to check. And all the previous ones to that, I think that they'd be worth checking if you had time. It's just that last one is kind of nasty to check to see if it works out. There's too many product rules and things to cancel out. I sincerely hope it's correct. Didn't lose any twos, different spots. So notice in this example we had to use integration by parts twice. But after the first iteration, after the first round, it was definitely better. So it was a good move to make. It just it took several not attempts, but several iterations. Okay, we can perform the same procedure for definite integrals using integration by parts. And I don't know if the procedure that I use in my section, in my class, for definite integrals aligns with the procedure used in other sections, but it should be okay. The way I do these is in 2 steps. In step 1, I ignore the bounds. I find the antiderivative. I give the antiderivative a name. I call it capital F of x. And it's just the question without bounds. Just ignore the e and the e to the 3. I want to find the antiderivative of ln of x dx. Okay, and we saw what the answer was from the beginning of the video. If you flip back, so I guess not flip back, but drag the time window back to the beginning, you'll see the answer is x ln of x minus x. But I want to show you where that comes from. I want to obtain it from scratch. What we'll do is we'll do integration by parts, even though it doesn't look like we can. So the late acronym, we have an L for sure, we have a log, so we let u equal ln of x. What's dv going to be equal to? Like, what's left? Nothing's left, just dx. You put a 1 in front of it if you want. There's always a 1 hiding there if you need it. So I'll add it, but not really needed. Okay, so because we're using integration by parts, let's put that somewhere. We're using IVP. We're going to get a replacement of that integral with uv minus the integral of v du. And we can plug in some of the pieces. We can plug in the u piece. So u, we said, was ln of x. Then we have to get the rest of the pieces. We have to get v, the space for that, and we have to get the du. Okay, so for the du, I'm going to take the derivative of ln of x. Du by dx is 1 over x. So du is dx over x. So dx over x goes here. Okay, now integrate dv to get v. V is the antiderivative of 1 with respect to x. So v is x. So we got an x there and an x here. That's kind of nice. We got an x times ln of x for the first term, minus the antiderivative of 1 with respect to x. Again, x over x is 1. And the antiderivative of 1 is just x. Antiderivative of 2 would be 2x. Antiderivative of 7 would be 7x. You get a plus c. But the plus c we can hide due to the bounds. I can hear screeching in the background, and it's a screeching of people who don't solve the definite integrals this way. Okay, so this is the first step, finding the general antiderivative. Step 2, evaluate it. Evaluate the antiderivative on the bounds. So that means we're going to calculate f of the top bound. So capital F evaluated at e to the 3. Calculate capital F at the bottom bound. So capital F evaluated at e and subtract them. So we'll have e to the 3 times the ln of e to the 3 minus e to the 3. So that's the top bound minus the bottom bound, plugging in e. E times ln of e minus e. And simplify. We get e to the 3 times 3 for the cancellation law, minus e to the 3 times 1, minus e times 1 minus e. Okay, so rewriting this in a slightly different way, we have 3e to the 3 minus e to the 3 minus 0. E minus e is 0. 3 of something minus 1 of something is 2 of that thing. So 2e to the 3 comes out as our final answer. Nothing simplifies it after that point. We can't bring the 3 down or anything like that. I see weird things happen sometimes with e's. But nothing weird can happen here. That's it. That's the answer. Underneath this, I want to write down a formula. We can also solve using the integral from a to b of u dv is equal to u times v evaluated from a to b minus the integral from a to b of v du. So what's happening here is we're taking the integration by parts formula, any derivative of u dv is equal to uv minus the integral of v du, and we're just evaluating each piece on the bounds from a to b. So if you're used to solving definite integrals all in one line, not in two steps, then you can use this formula. You're used to seeing this notation with a and the b. It'll work out to give you the same answer. Okay, so here's another problem. We want the antiderivative of x times sine of x evaluated from 0 to pi over 2. I'm going to split this up in two steps. So step 1, integral, we're going to find capital F of x, which is the antiderivative without bounds, x sine of x dx. So this is an invitation to use IPP. The late acronym, we don't have a log, but we do have an algebraic. So u is going to be equal to, the algebraic comes before the trig, so u is equal to x. dv is everything else. In this case, it's sine of x dx. Everything's accounted for, and I'll apply them together. So u we can put in as x, leave a space for v, a space for the v and the du. Okay, so du by dx is 1. That means du is equal to dx. That's nice. Now we have to get v. Integrating dv, integral of sine of x dx is negative cosine of x. Remember, we're taking the antiderivative, not the derivative. So negative cosine of x, and then another negative cosine of x over here. Things clean up. We get negative x cos x plus integral of cos of x. Dx. So negative x cos of x plus sine of x plus c. Since the derivative of sine is cos, the antiderivative of cos is sine. Okay, that's our answer. We can hide the plus c, bounds. So the plus c will just cancel if we include it. Might as well get rid of it. Now we'll go to step 2. Evaluate the antiderivative on the bounds. Evaluate capital F at the top number at pi over 2 minus capital F at the bottom number. Capital F of 0. Okay, so at pi over 2 we have negative pi over 2 times the cos of pi over 2 plus the sine of pi over 2. That's the top bound, minus the bottom bound, plugging in 0, negative 0 times the cos of 0 plus the sine of 0. Okay, so negative pi over 2 multiplied by 0, cos of pi over 2 is 0, sine of pi over 2 is 1 minus 0 times 1. I'll put the negative there. The negative's still there, I guess. Plus 0. So cos of 0 is 1, sine of 0 is 0, cos of pi over 2 is 0, sine of pi over 2 is 1. We can make sense of that from the cast rule. Or thinking about triangles being scrunched down. Whatever way you have, if you've decided to memorize those things or figure those things out. So 0 plus 1 minus 0. We get 1 as our answer. Okay, last problem. It's a multiple choice style question. So it's asking which of the following expressions is equivalent to the expression given. Integral from 0 to pi over 4 of x times secant squared of x. So those of you who use the other method, who do everything in line, have a slight advantage in this problem. You're not doing step 1, step 2. So I'm going to write that down after doing the step 1, step 2 method. I'll leave a little space at the bottom for it. Doing that way. It's good for the soul of everyone to learn more than one approach. I think it's, even though you're not going to necessarily adopt both methods and flip between them randomly, I think it's good for you to see multiple ways to solve questions. So if we use the step 1, step 2 method, I'm first going to find the antiderivative. X times secant squared of x dx, ignoring the bounds. Because we are inside section 7.1, the choice of method seems naturally to be integration by parts. It's harder when you don't know what section the question is in. Might try substitution, like try u is equal to secant squared and then do the whole du by dx and try and do a complete substitution. Not a good idea. But we'll let you try it if you want. Okay, the late acronym. What do we have in here? We have an algebraic before the trig. The late acronym says let u equal x. That means dv must be everything else. Secant squared of x dx. Okay, where does this take us? uv minus the integral of v du. So u we have as equal to x. V, we'll have to find that, leave a space for it. Minus the space for that stuff. Okay, let's go, let's see. Du by dx is 1. And that means du is equal to dx. So we'll put that in here. There's your dx. Place the du. Now dv. v is the integral of secant squared. What do you take the derivative of to get secant squared? The answer is tan. So x tan of x minus the integral of tan of x dx. Okay, in the end, then the question is answered. So we have a minus here, and a minus here. We have a plus, a minus, and a minus. So, looking at those, option B is wrong. It's got the wrong function. Option C is wrong. It's got the wrong function. It's got plus secant squared. Now option D has the minus, but it has a x in there, which doesn't match. And then option E has the secant, which doesn't match. It's a tan. So it must be option A. I'm going to move on to step 2, even though we didn't finish this. So step 1, I skipped a part of step 1 is calling this thing capital F. Step 2, what is f of the top bound, f of pi over 4 minus f of the bottom bound, f of 0. So that would be pi over 4 times the tan of pi over 4 minus 0 tan 0 minus integral from 0 to pi over 4 of the tan of x. So just evaluating all the pieces, taking the x tan x, evaluating it pi over 4, evaluating it 0 and subtracting, and then the integral has to be evaluated from 0 to pi over 4. Tan of pi over 4 is 1. Tan of 0 is 0, not that it matters, it's multiplied by 0. And we get exactly what's inside the expression, pi over 4 minus integral from 0 to pi over 4 tan of x dx. If you wanted to continue, if you want to fully solve this, even though you don't have to because it's multiple choice, tan of x is sine over cos, and then let w equal cosine of x, or let u equal cosine of x, and do substitution. But the question didn't require that. It required us to halfway integrate. Okay, underneath, method 2. Integral from 0 to pi over 4 of x secant squared x dx is going to equal to uv evaluated from 0 to pi over 4 minus the integral from 0 to pi over 4 of x secant squared of x dx. I'm going to recycle the work up above that we already did, so it's don't forget that we do have to do the work up above to solve this question this way, because I don't want to write it again, mostly for space reasons. So x, and then v is tan of x. And this notation that's there means evaluate it at the top number, evaluate the bottom number, and subtract. It's the f of a minus f of b in a different form. What am I doing? It's v du. Sorry about that. Okay, so v times du. V we have is tan of x. Du we have as dx. Okay, now we do the evaluation step. We have pi over 4 times tan pi over 4 minus 0 tan 0 minus integral from 0 to pi over 4 tan of x dx. Now we get what we got previously, pi over 4 minus integral from 0 to pi over 4 of tan of x. So a little bit easier to do because you don't have to realize to stop part way like we had to do in the other using the other method. But both methods will work. Okay, and that's it, your homework. Originally the homework included questions 55 and 57, so they're no longer part of the homework that's been assigned. You can skip them, but if you want to do them, oh wait, maybe I'm wrong. I'll check that. I can't remember. It may have been 35 and 37. I just can't remember. Anyway, there will also be a worksheet posted that will contain problems from 7.1, so look forward to that. Next video will be on section 7.6, which is improper integrals.